Tonight, a fascinating question drifts across the stars. If the universe may be filled with countless civilizations, why has none of them ever reached Earth? Across distances so vast that even light needs years, centuries or millennia to cross them, the dream of interstellar travel begins to collide with the laws of physics themselves. The deeper scientists look, the more impossible the journey appears. Before settling in for tonight's voyage through the cosmos, please take a moment to like this video, subscribe to Cosmic Bedtime Stories, and join us for more relaxing journeys through space science and the mysteries of the universe. Now, as the stars slowly emerge overhead, let's explore why aliens may never be able to reach Earth at all. The cosmic distance scale exists as a layered structure that describes how matter is separated across the universe from nearby stars to distant galaxies and beyond, into regions where light itself takes millions or billions of years to travel through space. The universe appears continuous, but it is divided into vast intervals defined by gravitational structure and the distribution of matter. Stars gather into galaxies, galaxies group into clusters, and clusters form superclusters, each level increasing the separation between individual systems in the outermost observable regions. Space is filled with extremely low-density gas and scattered particles, leaving enormous empty volumes between stellar systems within a single galaxy. The average distance between stars is measured in light years, a light year being the distance light travels in 1 year under constant speed in vacuum. This unit becomes essential because ordinary terrestrial measurements cannot describe such vast separations. The nearest star system lies several light years away, while most stars in the Milky Way are separated by distances far greater than simple intuition can easily grasp beyond the galaxy. Scale distances increase dramatically, where entire galaxies drift apart within the expanding fabric of space itself. This expansion means that space between galaxies grows over time, making intergalactic travel increasingly difficult. Even in principle, within this structure, any hypothetical journey from one star system to another must pass through regions of near vacuum where matter is sparse and interactions are rare. Yet even these empty regions contain faint radiation fields and diffuse hydrogen that fill the gaps between denser structures. This outer cosmic environment establishes the fundamental backdrop against which all motion must occur, and it defines the initial constraint that any interstellar traveler would face before even considering propulsion or direction. The sheer scale of separation ensures that distances are not merely large but fundamentally transformative in how motion and time are experienced within this outermost layer. The idea of crossing space becomes less about simple movement and more about enduring a prolonged existence through vast emptiness, where the absence of nearby structures defines the experience of distance itself. In this context, interstellar space is not empty in an absolute sense, but instead represents a medium where density approaches extremes far below any vacuum achievable on Earth. Scales, particles exist as isolated traces separated by distances that render collisions rare over human timescales. Yet when viewed across astronomical spans, these sparse particles still accumulate into meaningful structure, influencing light radiation and gravitational behavior. The distribution of matter within this scale follows patterns shaped by gravity, which acts over immense distances, drawing gas and dust into filaments and clouds that later become sites of star formation. These processes occur over millions to billions of years, reinforcing the slow evolving nature of cosmic structure. Within these vast spaces, light itself becomes the primary messenger, carrying information across distances that no physical object has ever crossed in full from one region to another. The delays inherent in this transmission mean that observation is always a view into the past rather than the present. reinforcing the separation between regions of space and the limits of simultaneity. Across cosmic scales, the structure of distance also defines how any hypothetical traveller would perceive motion where local movement appears slow, but cumulative distances become overwhelming when scaled to interstellar proportions. The outer regions of space therefore establish not only physical separation, but also a conceptual barrier between nearby environments and distant systems, reinforcing the idea that space travel at such scales is fundamentally different from any movement experienced within planetary boundaries. As these distances accumulate, the challenge of crossing them becomes not only a matter of speed, but also a matter of endurance across time and space itself. The vastness of the cosmic distance scale thus establishes the foundational reality that any interstellar journey must confront from its very beginning, shaping every subsequent limitation that emerges in deeper layers of physical and biological constraint. At these extreme scales, even familiar concepts such as direction and proximity begin to lose their intuitive meaning, because every reference point is separated by distances that dwarf planetary systems. The sense of near and far becomes dependent entirely on comparative measurement rather than direct experience within the Milky Way. For example, regions that appear densely populated in telescopic images are still separated by vast voids where no significant matter exists. The human mind tends to compress these separations into simplified images, yet the actual scale remains far beyond direct comprehension. This mismatch between perception and reality becomes increasingly important when considering any form of movement through space, because the effort required to traverse even small fractions of interstellar distance grows exponentially with scale rather than linearly. The structure of space itself remains continuous, but the effective challenge of crossing it increases with every additional layer of separation. The outer cosmic regions therefore represent not just physical space, but also a framework that determines what kinds of motion are realistically possible within known physics. The vast emptiness between stars acts as both a medium and a barrier, shaping how energy and matter interact across scales that extend far beyond any localized environment. In this way, the cosmic distance scale forms the first and most fundamental layer in understanding why movement across stars is not simply a matter of travel, but instead a transformation of scale itself, requiring conditions that extend far beyond ordinary physical experience and into regimes where distance becomes a defining feature of reality rather than just a measure between points in space. This framework sets the stage for understanding how isolation increases as systems become more distant, and how even the most advanced hypothetical travel methods must contend with the unchanging structure of separation that defines the observable universe. The deeper implication is that distance itself is not passive, but actively shapes the possibilities of motion and communication across all regions of space. Within this perspective, every attempt to cross interstellar space must begin with an acknowledgement of scale that far exceeds planetary experience and extends into regimes where distance defines not only separation, but also the fundamental limits of traversal itself, shaping all future possibilities for movement beyond a single star system in the universe. The speed of light limit defines the outer boundary of motion within the universe, and acts as a fundamental constraint on how information, energy, and matter can propagate through space. Light in vacuum travels at a fixed maximum speed, and this value remains constant for all observers regardless of their own motion or the motion of the source. This property emerges from the structure of space-time itself, where space and time are linked in a single framework that determines how events relate to each other. Within this framework, no physical object with mass can reach or exceed the speed of light, because doing so would require infinite energy, a condition that cannot be satisfied in any physical system known to physics. As velocity increases toward this limit, the energy required to continue accelerating grows rapidly, not in a simple proportional way, but in a sharply increasing curve that becomes unbounded as the speed approaches the maximum limit. This behavior is not a limitation of engineering, but a direct consequence of the geometry of space-time. As motion approaches relativistic speeds, time itself begins to behave differently relative to slower-moving observers. Time dilation occurs, meaning that time passes more slowly for an object moving close to the speed of light compared to an observer at rest. This effect has been measured experimentally using atomic clocks on fast-moving aircraft and satellites, confirming that time is not absolute, but depends on relative motion. In the context of interstellar travel, this means that any spacecraft approaching such speeds would experience time at a different rate than the surrounding universe. However, even this effect does not remove the fundamental barrier of the speed limit, because reaching distant stars would still require travel times measured in years, decades, or far longer depending on distance. The speed limit of light also defines the structure of causality in the universe. Events are connected through signals that cannot travel faster than this limit, ensuring that cause and effect remain consistent across all regions of space. If information could move faster than light, it would create situations where effects could appear before their causes, breaking the logical order of physical processes. The restriction preserves a consistent timeline for all observers and ensures that the universe remains predictable in its fundamental structure. This causal order extends across all scales from subatomic interactions to the motion of galaxies, making the speed of light not only a physical constraint, but also a foundational rule of reality. In interstellar terms, this limit transforms vast distances into equally vast timescales. A signal traveling at light speed still requires years to cross even the nearest stellar distances, meaning that communication and travel are both inherently delayed across cosmic scales. The nearest star system, located several light-years away, represents a delay of several years, even for the fastest possible transmission of information. More distant regions of the galaxy require tens of thousands of years for signals to arrive, and intergalactic distances extend this delay into millions of years. This creates a natural separation between regions of the universe that cannot be bridged instantaneously, or even within a single human lifetime. The structure of space-time also ensures that as objects approach the speed of light, their effective mass increases from the perspective of an outside observer. This increase in relativistic mass means that more and more energy is required for each incremental gain in speed. As a result, acceleration becomes progressively less effective, and the ability to approach the speed limit diminishes as the limit is approached. This creates a practical barrier long before the theoretical limit is reached, since the energy requirements quickly exceed any conceivable source available within known physical systems. Even the most energetic astrophysical phenomena such as supernovae or active galactic nuclei operate within the same constraint and cannot violate this boundary. The speed of light also influences how space and time are measured together. At relativistic speeds, distances contract in the direction of a motion. From the perspective of the moving object, a phenomenon known as length contraction. This means that space itself appears compressed for an object moving close to light speed, reducing the measured distance between 2 points in that frame of reference. However, this effect does not eliminate the overall travel time when considered from a universal perspective, because the constraints of acceleration and energy remain unchanged. The geometry of space-time adjusts in such a way that all observers agree on the underlying physical laws, even if their measurements of distance and time differ. Within this framework, the universe enforces a consistent limit on how quickly any interaction can propagate. This ensures that no region of space can become causally disconnected in a way that would allow instantaneous influence across arbitrary distances. Even gravitational effects, which are mediated through the curvature of space-time, propagate at the same speed limit. This was confirmed through observations of gravitational waves, which travel at light speed and carry information about distant cosmic events such as the merger of black holes. These observations reinforce the idea that the speed of light is not limited to electromagnetic phenomena, but applies universally to all known interactions. For hypothetical interstellar travelers, this limit establishes a permanent boundary on the experience of motion. No matter how advanced a propulsion system might become, it must still operate within this universal constraint. The energy required to approach the limit increases without bound, and the effects of relativistic physics become dominant long before the limit is reached. This ensures that the universe maintains a consistent structure where distance and time remain deeply interconnected, and where motion across vast regions of space always requires significant durations. The speed of light therefore acts not only as a maximum velocity, but also as a defining feature of how reality itself is organized across all scales. As this constraint operates throughout the cosmos, it shapes every possible path that matter or information can take, embedding itself into the structure of motion itself, and ensuring that no region of space can be reached without respecting the fundamental relationship between energy, time, and distance that defines the universe at its deepest level. Energy requirements for interstellar travel emerge directly from the structure of motion at high speed and the enormous scale of separation between stellar systems. Within known physics, any object with mass requires energy to accelerate, and that energy increases sharply as velocity approaches the speed of light. This relationship means that the closer a spacecraft moves toward relativistic speeds, the more energy is required for each additional increase in velocity. The result is not a gradual limitation, but a rapidly escalating barrier where small gains in speed demand disproportionately large amounts of energy. In the context of interstellar distances, this becomes the central constraint on any attempt to leave a star system and reach another within a meaningful timescale. The energy scale of everyday motion on Earth is negligible compared to what is required for even modest fractions of light speed. Chemical reactions, such as those used in conventional rocket fuels, release energy through rearrangement of atomic bonds. These processes are sufficient for launching spacecraft from planetary surfaces and sending probes across the solar system, but they are fundamentally limited in their energy density. The total energy stored in chemical fuels is many orders of magnitude lower than what would be required to accelerate a spacecraft to even a small fraction of the speed of light. This gap between chemical energy and relativistic energy requirements creates an immediate mismatch between known propulsion methods and the demands of interstellar travel. More advanced energy sources exist in theory and in astrophysical environments. Nuclear fission releases energy by splitting heavy atomic nuclei, while nuclear fusion releases energy by combining light nuclei into heavier ones. Fusion reactions power stars and represent one of the most efficient natural energy sources known. Even so, the conversion of nuclear energy into usable propulsion still faces limitations in efficiency control and waste heat management. In a stellar environment, fusion occurs under extreme pressure and temperature conditions that are not easily replicated or sustained in engineered systems. Although fusion-based propulsion has been studied as a potential pathway for interstellar probes, the energy still falls far short of what would be needed for large spacecraft carrying significant payloads to reach nearby stars within human timescales. The energy required for relativistic travel increases in a way that reflects the geometry of spacetime itself. As velocity increases, a growing portion of the input energy contributes not to further acceleration, but to relativistic effects such as increased momentum and effective inertia. This means that beyond a certain threshold, additional energy produces diminishing returns in terms of speed increase. Instead, the energy becomes increasingly absorbed into the relativistic structure of motion, rather than translating into simple velocity gains. This behavior ensures that the speed of light remains an unattainable boundary for any object with mass, regardless of energy availability. When scaled to interstellar distances, the implications of these energy requirements become even more pronounced. Even the nearest star system represents a separation measured in light years, and reaching it within a human lifetime would require sustained travel at a significant fraction of light speed. Achieving such speeds would demand energy sources far beyond those currently available on Earth, or within typical planetary environments. The total energy output of an entire planet over extended periods would be required to accelerate even modest spacecraft to the necessary velocities, and this does not include the energy needed for deceleration upon arrival, which would effectively double the requirement. Astrophysical observations show that even the most energetic natural events in the universe operate within the same physical limits. Supernovae release vast amounts of energy as massive stars collapse and explode, briefly outshining entire galaxies. Active galactic nuclei powered by supermassive black holes convert gravitational energy into radiation with extreme efficiency. Despite these immense outputs, they are distributed over vast volumes of space and time, and they are not naturally directed or controlled in a way that could be harnessed for precise interstellar propulsion. The scale of energy required for controlled travel remains distinct from the scale of energy released in uncontrolled cosmic events. Another constraint arises from the inefficiency of energy conversion. No known system converts energy into motion with perfect efficiency. In any realistic propulsion system, a portion of energy is lost as heat radiation or other forms of waste energy. As velocity increases, these inefficiencies become more significant because the energy demands rise faster than the ability to manage or dissipate excess heat. This creates a secondary limitation where not only is energy scarce, but the management of that energy becomes increasingly difficult as speed increases. The structure of space itself also plays a role in energy requirements. Interstellar space is not completely empty, and at high velocities even sparse particles become significant obstacles. Collisions with interstellar dust or gas particles at relativistic speeds would release large amounts of energy upon impact, requiring additional shielding and energy expenditure to protect any spacecraft. This shielding would itself add mass, further increasing the energy required for acceleration, creating a feedback loop where protection increases energy demand, and increased energy demand reinforces the need for more robust systems. From a broader physical perspective, energy in the universe is conserved and distributed across many forms, including mass radiation and gravitational fields. Transforming energy from one form to another always involves losses and constraints imposed by thermodynamic laws. These laws ensure that no process can operate with complete efficiency or without producing entropy. In the context of interstellar propulsion, this means that every stage of energy conversion introduces additional limitations that compound the overall challenge of reaching distant stars. Even hypothetical energy sources that go beyond current human technology, such as matter-antimatter annihilation, remain constrained by the same fundamental principles. While matter-antimatter reactions release large amounts of energy per unit mass, the production, storage, and containment of antimatter introduce severe practical limitations. Additionally, converting this energy into directed propulsion without excessive loss remains an unresolved engineering challenge. The scale of energy required for sustained relativistic travel still exceeds what could be reasonably harnessed or controlled even under optimistic theoretical assumptions. Ultimately, the energy requirements for interstellar travel reflect the deep structure of the universe itself. Motion at high speed is not simply a matter of overcoming resistance, but of interacting with the geometry of space-time where energy, mass, and velocity are tightly linked. This structure ensures that as attempts are made to reach farther distances in shorter times, the cost in energy increases beyond practical limits. The universe therefore enforces a balance between distance and energy that shapes all possible forms of motion across cosmic scales, making interstellar travel not only a question of engineering, but a direct expression of physical law operating at its most fundamental level. Propulsion technology defines how motion is generated in space, but across interstellar distances, every known and theoretical method encounters the same underlying constraints imposed by energy, momentum, and the structure of space-time. In the outermost practical sense, propulsion begins with the idea of expelling mass or energy in one direction to produce motion in the opposite direction. This principle, based on conservation of momentum, governs all rocket systems from simple chemical engines to advanced nuclear concepts. Even in the vacuum of space, where there is no atmospheric resistance, propulsion still depends on internal energy conversion and reaction mass to produce thrust. Chemical propulsion represents the most familiar and widely used technology for space travel. It relies on stored chemical energy released through combustion, producing high-speed exhaust gases that generate thrust. While highly effective for leaving planetary surfaces and navigating within a star system, chemical propulsion is fundamentally limited by the relatively low energy density of chemical reactions. The exhaust velocities achievable through chemical means are far below what would be required for interstellar travel. Even if optimized to theoretical limits, chemical systems cannot approach the fraction of light speed needed to make interstellar distances manageable within practical timescales. Beyond chemical propulsion, nuclear fission introduces a higher energy density source by splitting heavy atomic nuclei. This process releases significantly more energy per unit mass than chemical reactions, making it more suitable for long-duration space missions. Fission-based propulsion concepts include nuclear thermal engines, where reactor heat is used to accelerate propellant, and nuclear electric systems, where reactor power generates electricity for ion propulsion. These systems increase efficiency and extend mission capabilities, but they remain constrained by the same fundamental limits of momentum transfer and waste heat management. The thrust produced is still relatively low compared to the energy required for relativistic travel. Fusion propulsion offers a more powerful theoretical alternative, drawing on the same process that powers stars. In fusion reactions, light nuclei combine to form heavier nuclei, releasing large amounts of energy in the process. In principle, fusion engines could achieve much higher exhaust velocities than chemical or fission systems, potentially enabling faster travel within a star system and more ambitious missions beyond it. However, controlled fusion remains an unresolved engineering challenge. Maintaining stable, sustained fusion reactions outside of stellar environments requires extreme conditions of temperature and confinement that are difficult to reproduce and control. Even if achieved, fusion propulsion would still face the relativistic energy barrier that limits acceleration at high speeds. More speculative propulsion concepts attempt to bypass traditional reaction mass entirely or minimize its use. Photon propulsion, for example, relies on the momentum carried by light itself. Since photons travel at the speed of light and carry momentum, Despite having no rest mass, a spacecraft emitting directed radiation can in principle generate thrust. However, because photons carry relatively small amounts of momentum per unit energy, achieving meaningful acceleration requires enormous energy input. This makes photon-based propulsion extremely inefficient for large spacecraft, particularly when scaled to interstellar requirements. Ion drives and plasma propulsion systems represent another class of advanced technology currently used in space exploration. These systems accelerate charged particles using electromagnetic fields, producing highly efficient but very low thrust. While they are valuable for long-duration missions within a star system, their low acceleration rates make them unsuitable for rapid interstellar travel. Even with continuous operation over extended periods, the velocities achieved remain far below what is required to significantly reduce interstellar travel times. All propulsion systems face a shared limitation rooted in the need to carry or generate energy internally. A spacecraft must either carry its own energy source or collect energy from external environments, but both approaches introduce constraints. Carrying energy increases mass, which in turn increases the energy required for acceleration. Collecting energy from external sources such as stellar radiation reduces the need for onboard fuel, but introduces limitations based on distance, intensity, and collection efficiency. These trade-offs create a structural boundary that prevents any propulsion system from escaping the fundamental relationship between mass energy and velocity. At relativistic speeds, propulsion becomes increasingly inefficient due to the growing dominance of kinetic energy requirements. As velocity increases, the energy required for further acceleration grows disproportionately, making each incremental gain more costly than the last. This means that even the most advanced propulsion systems would experience diminishing returns long before approaching the speed of light. The transition from classical to relativistic motion marks a shift where traditional engineering intuition no longer applies in a straightforward way, and where energy input no longer translates efficiently into increased velocity. Another critical limitation arises from thermal management. All propulsion systems generate waste heat as a byproduct of energy conversion. In space, heat can only be dissipated through radiation, which becomes increasingly inefficient as power levels rise. High-energy propulsion systems must therefore manage not only thrust generation, but also the removal of excess heat. At interstellar energy scales, this becomes a major engineering barrier, as radiators and cooling systems would need to be extremely large and efficient, adding additional mass and complexity to any spacecraft design. Structural materials also impose constraints on propulsion technology. The stresses involved in high acceleration or high energy systems require materials capable of withstanding extreme temperatures, radiation, and mechanical forces. While modern materials science has developed increasingly advanced alloys and composites, all known materials ultimately degrade under sustained extreme conditions. This limits the maximum performance envelope of any propulsion system and adds another layer of restriction to interstellar travel feasibility. Even hypothetical propulsion methods that rely on exotic physics remain constrained by conservation laws and relativistic limits. Concepts such as warp drives or space-time manipulation remain speculative and require conditions or forms of energy that have not been observed in practical systems. While they are studied theoretically within the framework of general relativity, they do not currently offer a viable or demonstrated pathway for faster-than-light travel. As a result, all known propulsion methods, whether practical or theoretical, remain bound within the same physical framework that governs motion in the universe. Within this framework, propulsion technology represents not a pathway to overcoming interstellar distance, but a series of increasingly refined methods of operating within fixed physical limits. Each advancement improves efficiency, range, or endurance, but none fundamentally alters the structure of space-time or the energetic cost of high-speed travel. The universe therefore maintains a consistent boundary on motion, ensuring that propulsion remains an expression of physical law rather than a means of transcending it. Interstellar dust and microscopic particles form a thin but persistent medium throughout space that becomes increasingly significant as velocity rises toward relativistic speeds. At first glance, interstellar space appears empty, with vast regions containing only a few atoms per cubic centimetre. However, this sparse material is not truly negligible when considered over interstellar distances, and especially not when considered at extreme velocities. Even a single grain of dust, often smaller than a fraction of a micrometer, carries enough mass to produce catastrophic effects when struck at a substantial fraction of the speed of light. The distribution of interstellar matter is not uniform. It exists in diffuse clouds, filaments, and regions shaped by stellar winds and supernova remnants. These structures contain hydrogen gas, helium, and trace amounts of heavier elements condensed into microscopic dust grains. Over time, these particles drift through galaxies, forming a background environment that permeates nearly all regions of interstellar space. Although the density is extremely low compared to planetary atmospheres, the cumulative presence of this material across vast distances creates a continuous hazard for any object moving through it at high speed. At everyday velocities within a planetary system, interstellar dust presents no meaningful danger. Spacecraft routinely pass through regions containing small particles without significant impact. However, as velocity increases toward a significant fraction of light speed, the nature of collisions changes fundamentally. Even isolated hydrogen atoms, which are the most common constituents of interstellar space, become high-energy projectiles when encountered at relativistic speeds. The energy released in such collisions scales with velocity, meaning that at extreme speeds even the smallest particles can deposit large amounts of energy into a spacecraft structure. Dust grains represent a more severe form of this hazard. These grains are composed of silicates, carbon compounds, and metallic elements, often forming irregular shapes with masses far greater than individual atoms. When a grain of dust collides with a spacecraft traveling at high velocity, the impact is not a simple mechanical collision, but a high-energy event that can vaporize material at the point of contact. The energy released in such an impact can produce localized plasma shock waves and intense thermal damage, all concentrated into extremely small areas. Repeated exposure to such impacts over interstellar distances would gradually erode or even destroy exposed surfaces. Shielding against interstellar dust introduces significant engineering challenges. Any protective barrier must be strong enough to absorb or deflect high-energy particles while not adding excessive mass to the spacecraft. Increasing shielding thickness improves protection but also increases mass, which in turn raises the energy required for acceleration. This creates a feedback loop where improved safety directly increases propulsion demands, reinforcing the fundamental energy barrier of interstellar travel. Even advanced shielding concepts such as layered or sacrificial materials cannot fully eliminate this trade-off. At relativistic speeds, even sparse gas becomes a source of continuous radiation exposure. Hydrogen atoms impacting a spacecraft at such velocities effectively behave like high-energy cosmic rays penetrating materials and generating secondary particle cascades. This radiation can degrade structural materials, damage electronic systems, and pose severe risks to any biological organisms on board. Over long durations, cumulative exposure becomes a critical limiting factor, requiring additional shielding that further increases mass and complexity. The interaction between dust and radiation creates a compound hazard. When high-speed particles strike shielding materials, they generate secondary radiation that spreads throughout the spacecraft's structure. This secondary radiation is often more difficult to mitigate than the initial impact, because it can penetrate deeper into materials and affect systems not directly exposed to the initial collision. As velocity increases, these effects become more intense, leading to a complex environment of cascading particle interactions that are difficult to control or predict in detail. Interstellar space is also influenced by stellar winds, which are streams of charged particles emitted by stars. These winds extend far beyond stellar systems and contribute additional charged particles to the interstellar medium. Although their density is low, their presence adds another layer of interaction for any high-speed spacecraft. At relativistic velocities, even these low-energy particles contribute to cumulative erosion and radiation exposure over time. The structure of the interstellar medium is shaped by astrophysical processes such as supernova explosions, stellar outflows, and gravitational interactions between gas clouds. These processes create regions of varying density, meaning that a spacecraft traveling through interstellar space would encounter changing environmental conditions rather than a uniform vacuum. Some regions may be relatively clear, while others contain denser concentrations of dust and gas that significantly increase collision risks. This variability adds uncertainty to long-distance travel, as exact environmental conditions cannot be fully predicted in advance over vast distances. As velocity increases, the effective impact energy of even the smallest particles becomes so large that traditional notions of shielding begin to break down. Materials that are strong under ordinary conditions may fail under continuous bombardment from high-energy impacts. At extreme speeds, the interaction between matter and shielding becomes dominated by plasma physics rather than solid-state mechanics, meaning that the protective layer itself may behave unpredictably under sustained exposure. The cumulative effect of these hazards is not limited to immediate structural damage. Over long durations, repeated impacts can alter the chemical composition of exposed materials, weaken structural integrity, and degrade system performance. Even if individual impacts are survivable, the long-term accumulation of damage becomes a limiting factor for mission duration. This gradual degradation imposes a temporal boundary on interstellar travel, where survival is constrained not only by speed and energy, but also by material endurance over time. From a broader perspective, interstellar dust transforms space from a simple vacuum into a dynamic environment filled with low-density but high-energy interactions at extreme speeds. While it remains nearly invisible on human scales, its significance increases dramatically when velocity rises. This transformation illustrates how physical reality depends not only on the presence of matter, but also on the conditions of motion through that matter. In this way, interstellar dust becomes a defining factor in shaping the limits of travel across cosmic distances, reinforcing the conclusion that even seemingly empty space imposes fundamental constraints on movement through it. The radiation environment of interstellar space forms an invisible but persistent field of energetic particles and electromagnetic waves that permeate the galaxy and extend far beyond any single star system. This environment is not static but continuously shaped by stellar activity, supernova explosions, and the behavior of charged particles moving through magnetic fields. At low velocities, its effects are subtle and often negligible for short-duration missions within a star system. However, as speed increases and exposure time extends across interstellar distances, radiation becomes one of the most significant limiting factors for any form of travel beyond a planetary neighborhood. Cosmic radiation originates from multiple sources. One major component is galactic cosmic rays, which are high-energy particles accelerated by supernova remnants and other energetic astrophysical processes. These particles include protons, helium nuclei, and heavier atomic nuclei that travel through space at extremely high energies. When they encounter matter, they can penetrate deeply into material's ionizing atoms along their path, and creating cascades of secondary particles. This process makes cosmic radiation particularly difficult to shield against, as it is not a single uniform form of energy, but a continuous spectrum of high-energy impacts. Another source of radiation is solar or stellar wind particles emitted continuously by stars. In the case of a star system like the one containing Earth, the solar wind forms a vast bubble known as the heliosphere, which partially shields the inner system from some external radiation. Beyond this protective region, interstellar space becomes more directly exposed to galactic radiation fields. Any spacecraft leaving a star system would lose this natural shielding and enter a more intense radiation environment that persists across interstellar distances. Electromagnetic radiation also fills space in the form of background fields such as the cosmic microwave background, a remnant of the early universe that exists uniformly throughout space. While this radiation is relatively low in energy compared to cosmic rays, it still contributes to the overall radiation environment and provides a constant low-level energy field that permeates all regions of space. Combined with higher energy particle radiation, it forms a complex background that any interstellar traveler must continuously endure. At relativistic speeds, radiation exposure becomes significantly more intense due to the effects of motion through particle fields. As velocity increases, incoming particles are effectively blue-shifted in the direction of travel, meaning their energy appears higher from the perspective of the moving spacecraft. This transformation increases the damage potential of each particle impact, turning relatively low-energy interstellar gas into high-energy radiation capable of penetrating shielding and damaging internal systems. This effect is not simply a matter of increased frequency, but a fundamental change in the energy distribution of encountered particles. The interaction between radiation and matter at high speeds leads to ionization cascades within materials. When a high-energy particle strikes a surface, it can dislodge electrons from atoms, creating charged particles that propagate through the material. These secondary particles can spread damage beyond the initial impact point, affecting electronic systems' structural integrity and any biological components present. Over time, this cumulative damage becomes a critical limitation for long-duration exposure in space environments. Biological systems are particularly sensitive to radiation exposure. Living cells can be damaged by ionizing radiation, leading to mutation, cell death, or long-term degradation of biological function. In the context of interstellar travel, even short-term exposure at high intensity could exceed survivable limits without substantial shielding. However, shielding against radiation at relativistic speeds requires increasingly dense and massive protective structures, which directly conflicts with the need to minimize mass for acceleration. This creates a structural trade-off where protection and mobility are in direct opposition. Radiation shielding in spacecraft typically relies on materials that absorb or deflect incoming particles. Hydrogen-rich materials are often considered effective because they can slow down and capture high-energy particles through repeated interactions. However, at extreme energies, even thick shielding layers become less effective because particles can penetrate deeply before interacting. Increasing shielding thickness improves protection, but also increases mass reinforcing the same energy constraints that limit propulsion systems. The interstellar radiation environment is not uniform. It varies depending on proximity to astrophysical sources such as supernova remnants, star-forming regions, and active galactic structures. Some regions of space may contain elevated radiation levels, due to recent energetic events, while others may be comparatively quieter. However, over the timescales required for interstellar travel, a spacecraft would likely encounter multiple variations in radiation intensity, creating a dynamic and unpredictable exposure profile. Magnetic fields in space also influence radiation behavior. Charged particles are deflected and guided by magnetic fields, creating complex structures in their distribution. While some regions may experience reduced particle density due to magnetic shielding effects, other regions may concentrate particles along field lines. A spacecraft traveling through these environments would experience varying radiation flux depending on its trajectory relative to these fields, adding another layer of variability to the radiation hazard. As velocity increases, relativistic effects alter the perception of radiation even further. Incoming radiation becomes increasingly concentrated in the forward direction of motion due to relativistic beaming. This means that instead of being evenly distributed around the spacecraft, radiation becomes focused into a narrow cone ahead of travel. This concentration increases the intensity of exposure in the direction of motion, making forward-facing surfaces particularly vulnerable to damage. This effect intensifies as speed approaches the speed of light, further compounding the challenges of high-velocity travel. The cumulative impact of radiation over interstellar distances is not limited to immediate damage. Long-term exposure can degrade materials, reduce the efficiency of electronic systems, and weaken structural integrity through gradual atomic displacement. This slow accumulation of damage creates a lifespan limitation for spacecraft systems independent of propulsion or energy constraints. Even if a spacecraft could maintain sufficient speed and energy, it would still face progressive degradation from radiation exposure over time. In the broader context of interstellar travel, radiation represents a continuous and unavoidable environmental constraint. It cannot be eliminated, only mitigated, and mitigation strategies always involve trade-offs with mass energy or complexity. The deeper implication is that space is not a neutral void, but an active energetic environment that imposes constant stress on any object moving through it. This persistent exposure ensures that long-duration travel across interstellar distances requires not only propulsion and energy management, but also continuous resistance against a pervasive and structurally unavoidable radiation field that defines the outer environment of the galaxy. Time dilation emerges from the structure of space-time itself, where time is not an independent background but a dimension interconnected with space. As motion increases toward the speed of light, the rate at which time passes begins to change relative to different observers. This effect is not a mechanical slowdown in a physical system, but a fundamental consequence of how measurements of time and space relate under high velocity. Within interstellar travel scenarios, this phenomenon becomes increasingly important, as velocities approach relativistic regimes shaping how journeys are experienced from both onboard and external perspectives. At ordinary speeds, time flows in a way that appears universal. Clocks on Earth, spacecraft in orbit, and distant astronomical systems all seem to progress at comparable rates when relativistic effects are negligible. However, precise measurements using atomic clocks have confirmed that even at relatively modest velocities, time dilation occurs. Clocks in fast-moving aircraft or satellites tick at slightly different rates compared to those on Earth, demonstrating that time is influenced by motion and gravitational fields. These differences are extremely small in everyday contexts but become significant as velocity increases. As speed increases further approaching a significant fraction of the speed of light, time dilation becomes much more pronounced. From the perspective of an external observer, a spacecraft moving at relativistic speed appears to experience time more slowly. Processes on board, including biological functions, mechanical operations, and even atomic transitions all appear to slow down relative to the outside universe. This means that while a journey may take many years in the external frame of reference, the onboard experience of time can be significantly shorter depending on the velocity achieved. This effect is symmetric in the sense that each observer sees the other as moving through time differently. However, the asymmetry arises when acceleration and deceleration are considered, particularly in travel scenarios involving departure and arrival between different regions of space. The practical outcome is that time experienced by travelers can diverge significantly from time experienced by those who remain stationary in a given reference frame. This difference becomes more extreme as velocity increases toward the speed of light. In the context of interstellar distances, time dilation introduces a complex relationship between travel duration and perceived time. A journey to a nearby star system may take many years when measured by external observers, but for travelers moving at very high speeds, the onboard experience could be significantly shorter. However, this does not eliminate the fundamental constraint of distance. Even if subjective time is reduced, the external universe continues to evolve, and the destination still requires traversal across vast spatial separations. Time dilation changes perception of duration, but does not remove the requirement for sustained motion through space. The mathematical structure underlying time dilation is tied to the geometry of space-time, where the relationship between space and time coordinates changes depending on velocity. As velocity increases, the contribution of time to the overall space-time interval shifts, resulting in slower progression of proper time along the path of the moving object. Proper time refers to the time measured by a clock moving with the object, and it becomes the relevant measure of experience for any traveller. This distinction between proper time and coordinate time is essential for understanding how different observers can disagree on the duration of the same journey while still remaining consistent within physical laws. Gravitational fields also contribute to time dilation. In stronger gravitational environments, time passes more slowly relative to regions with weaker gravity. This has been observed in systems such as satellites orbiting Earth, where clocks at higher altitudes experience slightly different rates compared to those on the surface. In interstellar contexts, variations in gravitational fields near stars, black holes, or dense astrophysical objects would further influence time progression. However, these effects are generally small compared to the extreme time dilation produced by relativistic velocities. As velocity increases closer to the speed of light, the energy required to continue accelerating grows rapidly, and time dilation becomes correspondingly stronger. In the limit where velocity approaches the speed of light, time for the moving object would appear to slow dramatically relative to external observers. However, reaching this limit is not physically achievable for objects with mass, meaning that time dilation, while significant, always remains finite in realistic scenarios. This ensures that interstellar travel, even under extreme conditions, cannot eliminate the passage of external time entirely. One of the most important implications of time dilation is its effect on synchronization between different regions of space. If a spacecraft were to travel to a distant star system and return, the elapsed time experienced on board could differ substantially from the time that passed on Earth or the origin system. This creates a form of temporal separation where travelers may return to a universe that has progressed far beyond their subjective experience. While this effect is well understood in physics, it introduces a deep separation between experience and external chronology in long-distance travel. Time dilation also affects communication. Signals sent between rapidly moving objects or between distant regions of space experience shifts in frequency and timing. These relativistic effects alter how messages are received and interpreted, creating delays and distortions that increase with velocity and distance. As a result, real-time communication becomes impossible across interstellar scales, and even relativistic travel introduces additional layers of temporal mismatch between sender and receiver. From a physical perspective, time dilation reinforces the inseparability of space and time. Motion through space is always accompanied by motion through time, and changes in one dimension affect the other. This relationship ensures that no trajectory through space-time can bypass temporal progression entirely. Even at extreme velocities, time continues to advance, ensuring that every journey has a duration measured within the structure of the universe itself. Within the broader context of interstellar travel time, dilation offers partial mitigation of subjective travel time, but does not resolve the underlying constraints of energy, distance, and radiation exposure. It changes the experience of motion without changing the fundamental requirements for traversal. The universe therefore maintains a consistent framework where time, like space, imposes structure and limitation on all possible motion, ensuring that even the fastest conceivable journeys remain embedded within the same physical laws that govern all processes across the cosmos. Biological constraints define a strict boundary on how living systems respond to prolonged exposure to space environments, and these constraints become increasingly severe as duration, velocity, and distance scale toward interstellar conditions. Life as known on Earth depends on stable chemical processes, regulated temperatures, controlled radiation exposure, and continuous energy intake. When removed from planetary conditions, each of these requirements becomes difficult to maintain, and the challenge intensifies further when travel extends across interstellar distances, where isolation and duration far exceed any human-built system tested so far. At the most fundamental level, biological systems are composed of cells that rely on tightly controlled chemical gradients. These gradients depend on liquid water, stable pressure ranges, and relatively narrow temperature conditions. In space, the absence of atmospheric pressure and the presence of extreme thermal variation disrupt these conditions. Without careful containment, water transitions rapidly between states, biological structures lose stability, and molecular processes that sustain life become increasingly difficult to regulate. Even within controlled spacecraft environments, maintaining these conditions requires continuous energy input and precise environmental regulation over long periods. Radiation exposure adds another layer of biological limitation. Living tissue is sensitive to ionizing radiation, which can break molecular bonds and damage DNA structures. Over short durations within planetary magnetic fields or shielded spacecraft, this exposure can be managed. However, in interstellar space, radiation levels increase significantly due to cosmic rays and high-energy particles that are not deflected by planetary magnetospheres. Over extended durations, cumulative exposure becomes a major risk factor for cellular damage, mutation accumulation, and long-term physiological decline. Shielding can reduce exposure but cannot eliminate it entirely without introducing significant mass and engineering complexity. Metabolism itself depends on continuous energy intake and waste removal. In closed systems, all biological processes must be supported by stored resources or regenerative life support systems. Oxygen, food, and water must be recycled or replenished, and waste products must be processed efficiently. On interstellar timescales, even highly efficient recycling systems face degradation, resource depletion, and system failure risks. The longer the duration of travel, the more likely it becomes that small inefficiencies accumulate into critical shortages or system breakdowns. This introduces a temporal limit to biological sustainability, independent of propulsion or navigation capability. Temperature regulation is another essential requirement for biological stability. Human biology operates within a narrow temperature range, and deviations from this range can quickly lead to dysfunction or failure. In space, temperature extremes are driven by exposure to solar radiation, shadowed regions, and internal heat generation within spacecraft systems. Managing these variations requires complex thermal control systems that must operate continuously without interruption. Over long durations, maintaining consistent thermal balance becomes increasingly difficult due to system-wear energy limitations and external environmental variability. Microgravity or near-weightless conditions also affect biological systems over time. In the absence of gravitational loading, muscles weaken, bone density decreases, and fluid distribution within the body shifts. These changes have been observed in astronauts during extended stays in orbit around Earth. While partial mitigation is possible through exercise and mechanical stimulation, long-duration exposure leads to progressive physiological adaptation that is not fully reversible. Over interstellar timescales, these effects would compound unless artificial gravity systems are implemented, which themselves introduce additional engineering complexity and energy requirements. The psychological and neurological dimensions of biological constraint are also significant. Isolation, sensory monotony, and prolonged confinement in limited environments can affect cognitive function and emotional stability. While not purely physical in nature, these effects are tied to the structure of biological processing in the brain, which depends on environmental stimulation and social interaction patterns evolved under planetary conditions. Over long durations, maintaining mental stability becomes as critical as maintaining physical health, especially when external contact is delayed or non-existent due to interstellar distances. Genetic stability introduces another layer of limitation. Over long periods, accumulated radiation exposure and cellular replication errors can lead to genetic mutations. While many of these changes are harmless or repaired by biological mechanisms increased, exposure raises the probability of harmful mutations affecting health or reproductive viability. In the context of multi-generational travel, these effects become especially relevant as small genetic changes may accumulate across generations in ways that are difficult to predict or control. Closed ecological systems required for interstellar travel must replicate Earth-like conditions within a fully sealed environment. This includes not only air and water recycling, but also food production, microbial balance, and long-term ecosystem stability. Even on Earth, ecosystems are complex and sensitive to change, and replicating such systems in a closed artificial environment introduces significant instability risks. Over long durations, small imbalances in biological cycles can lead to cascading failures that are difficult to correct once established. As biological constraints accumulate across multiple systems, cellular, metabolic, environmental, neurological, the overall resilience of living organisms decreases over time in isolated space conditions. Each system depends on the stability of others, meaning that failure in one area can propagate through the entire biological network. This interconnected vulnerability makes long-duration survival increasingly uncertain, even under advanced technological support. Within the broader framework of interstellar travel, biological constraints represent a fundamental mismatch between evolved life and the conditions of deep space. Life on Earth developed under stable gravity, atmospheric protection, and continuous ecological cycles, while interstellar space offers none of these stabilizing factors. Even with advanced engineering, biological systems remain bound by their underlying chemical and physical requirements, which cannot be fully separated from environmental conditions. This creates a deep structural limitation where survival over interstellar distances depends not only on technology, but on sustaining complex biological equilibrium over time periods far beyond any currently observed human experience. As all supporting systems degrade slowly but continuously under space conditions, biological persistence becomes one of the most fragile components in the entire framework of interstellar travel, reinforcing the broader conclusion that living organisms face intrinsic limits when removed from planetary environments for extended durations. Generation ship concepts emerge as a response to the extreme distances between star systems and the impossibility of completing interstellar journeys within a single human lifetime under known physical constraints. A generation ship is a self-contained environment designed to sustain human life across many successive generations while traveling slowly through interstellar space. The vessel itself becomes a miniature isolated world, carrying not only passengers, but also the full ecological, technological and cultural systems required to maintain life over centuries or even millennia. In theory, such a system allows biological continuity across timescales that exceed individual lifespans, but in practice it introduces layers of complexity that grow over time rather than diminishing. The outer structure of a generation ship must provide protection against the interstellar environment, including radiation, micrometeoroid impacts and thermal variation. This requires a durable hull capable of withstanding slow but continuous degradation over extremely long durations. Even minor damage accumulation becomes significant when extended across centuries, as small structural weaknesses can evolve into larger failures if not continuously monitored and repaired. The outer shell therefore functions not only as a barrier but also as a long-term maintenance system that must remain functional without external support. Inside this protective layer, the environment must replicate essential Earth-like conditions. Air composition must remain stable, water must be continuously recycled, and temperature must be regulated within narrow biological limits. These requirements depend on closed-loop ecological systems that recycle waste, regenerate oxygen, and sustain food production. While such systems exist in limited experimental forms, scaling them to a fully self-sustaining multi-generational environment introduces significant instability risks. Biological cycles must remain balanced across long periods, and even small deviations can accumulate into larger systemic failures. Agricultural systems within the generation ship must operate continuously without interruption. Plant growth, nutrient cycling, and microbial balance form interdependent networks that support the human population on board. These systems rely on predictable environmental conditions, yet over long durations. Small fluctuations in light levels, temperature, or resource distribution can alter growth patterns. Maintaining stability requires constant monitoring and adjustment, and even with advanced automation, the risk of gradual imbalance remains present across generational timescales. Population dynamics represent another critical constraint. A generation ship must maintain a stable population size that is large enough to preserve genetic diversity, but small enough to remain sustainable within available resources. If the population is too small, genetic bottlenecks may occur, increasing the risk of inherited conditions and reducing long-term viability. If the population is too large, resource consumption may exceed sustainable limits within the closed system. Balancing these factors over multiple generations introduces uncertainty that compounds over time, especially when demographic fluctuations occur naturally. Social continuity becomes increasingly complex in isolated environments where external reference points are absent. Over long durations, cultural, linguistic, and institutional structures evolve independently of their original context. While this evolution is a natural feature of human societies within a generation ship, it may lead to divergence from initial mission parameters. knowledge transmission across generations must remain stable to ensure that technical systems continue to function. Yet historical examples of isolated communities suggest that knowledge can degrade, fragment, or transform when not reinforced by external contact. Technological maintenance within a generation ship depends on sustained industrial capacity. Machines' life support systems and ecological infrastructure all require ongoing repair and replacement of components. Over centuries, manufacturing systems must remain operational, including the ability to process raw materials, fabricate parts, and manage energy distribution. Any breakdown in industrial capability could cascade into multiple system failures, as interdependent technologies rely on continuous maintenance cycles. The absence of external supply chains makes internal resilience the only available support mechanism. Energy production within a generation ship must be continuous and reliable. Nuclear systems, solar collection in deep space, or other advanced energy sources would need to operate over extremely long durations without interruption. Energy storage systems must also buffer fluctuations in supply and demand. Over time, even small inefficiencies in energy conversion or storage degradation could accumulate into shortages, placing additional stress on all life support systems. Navigation and trajectory maintenance remain essential even for slow interstellar travel. A generation ship must maintain a stable course over long periods, adjusting for gravitational influences, interstellar medium interactions, and cumulative drift. While space may appear empty, subtle forces can alter trajectories over time, requiring periodic correction. These corrections depend on reliable propulsion or guidance systems that must function across generations without external recalibration. Psychological and institutional stability becomes increasingly important in isolated long-duration environments. Over time, human perception of mission purpose may shift as successive generations become further removed from the original departure context. Without external contact, motivation, governance structures, and shared goals must be maintained internally. Historical patterns of isolated communities suggest that social systems can adapt in unpredictable ways when removed from broader civilization, introducing uncertainty into long-term mission coherence. Genetic management also becomes a central concern in closed populations. Over many generations, genetic drift can alter the distribution of traits within the population. Even with careful selection and management, random variations accumulate over time. Maintaining long-term biological health requires continuous monitoring and potentially active intervention to preserve genetic diversity and reduce the impact of inherited conditions. As all these systems interact, generation ships become highly complex, self-regulating environments, where biological, technological, and social factors are tightly interwoven. Each subsystem depends on the stability of others, creating a network of dependencies that must remain balanced over extremely long periods. Small disruptions in one area can propagate through the entire system, leading to cascading effects that are difficult to reverse in a closed environment. Within the broader context of interstellar travel generation, ships represent a conceptual bridge between human biological limitations and the vast distances separating star systems. However, they do not remove the underlying constraints of energy, radiation, ecological stability, and time. Instead, they redistribute these constraints across generations, transforming a single journey into a continuous process of maintenance and adaptation across centuries. This transformation does not eliminate the difficulty of interstellar travel, but extends it across time, reinforcing the fundamental reality that survival and continuity in deep space remain deeply dependent on maintaining fragile systems far from any external support. Communication across interstellar distances becomes fundamentally constrained by the same structure of space-time that governs motion, energy, and causality. At its core, communication relies on the transmission of signals, and all known signals propagate at or below the speed of light. This universal limit ensures that no information can travel instantaneously between distant points, meaning that any exchange between star systems is inherently delayed. As distances increase to interstellar and intergalactic scales, these delays grow from years into centuries and eventually into millions of years, transforming communication into a slow and asynchronous process rather than a real-time interaction. Within a single star system, communication delays are often negligible for practical purposes. Signals between planets or spacecraft can be transmitted and received within minutes or hours depending on distance. However, once communication extends beyond a star system, the delay becomes a defining feature of interaction. A message sent to a nearby star system requires several years to arrive, and a response requires an equivalent amount of time to return. This creates a structure where dialogue becomes fragmented across long periods, with each exchange separated by significant temporal gaps. The finite speed of light ensures that all electromagnetic signals, including radio waves and optical transmissions, are subject to the same delay constraints. Even the most advanced communication technologies cannot bypass this limitation, because it is not dependent on engineering but on the fundamental properties of spacetime. As a result, increasing signal power or improving transmission efficiency does not reduce travel time. It only affects signal clarity and detectability across vast distances. In interstellar context, this delay transforms communication into a form of historical exchange. Messages received from distant systems always reflect conditions from years or centuries in the past, meaning that any response is directed toward a previous state of the sender rather than their current condition. This temporal disconnect introduces a persistent lag between information and reality, making coordinated interaction between distant systems inherently outdated by the time it is received. As distance increases further, the structure of communication begins to break down into isolated information pockets. Within a single galaxy, communication between distant regions becomes impractically slow for coordinated decision-making on short timescales. Across intergalactic distances, communication delays exceed the timescales of civilizations, making meaningful interaction effectively impossible within any shared temporal framework. This creates a universe where regions of space evolve independently connected only by extremely delayed exchanges of information. Relativistic effects further complicate communication when one or both parties are in motion at high velocity. Time dilation alters the rate at which messages are sent and received, while Doppler shifting changes the observed frequency of signals. A spacecraft moving at relativistic speed may experience incoming signals as compressed or stretched in frequency, depending on direction of travel. These effects distort communication patterns, making interpretation more complex and requiring constant adjustment for relativistic corrections. Directional communication also becomes constrained by the expansion and structure of space itself. As the universe expands, distant regions move away from each other at increasing rates. In some cases, this expansion can cause regions of space to recede faster than light due to the expansion of space rather than motion through space. In such regions, signals emitted from one area may never reach another, effectively creating communication horizons beyond which information exchange is impossible. This introduces a natural boundary to connectivity across the universe, not due to technological limitation, but due to cosmological structure. Signal degradation is another limiting factor over extreme distances. As electromagnetic waves travel through interstellar and intergalactic media, they interact with particles, magnetic fields, and gravitational effects that can scatter or distort the signal. Although space is mostly transparent over vast distances, even minimal interference can accumulate, reducing signal strength and clarity. This means that distant communication is not only delayed, but also increasingly difficult to detect and interpret accurately. Energy requirements for communication also increase with distance and signal strength. To ensure detectability across interstellar scales, signals must be transmitted with sufficient power to overcome dispersion and noise. However, generating and directing such high-energy signals requires substantial energy resources, which must be balanced against other needs such as propulsion, life support, and system maintenance. This creates a trade-off between communication reach and resource allocation, particularly for isolated spacecraft or civilizations operating far from energy-rich environments. The concept of real-time coordination becomes fundamentally impossible across interstellar distances. Any attempt to synchronize actions between distant systems is limited by the time it takes for information to travel. Decisions made in one location cannot immediately influence another, and by the time responses are received, conditions may have already changed significantly. This leads to a form of autonomous development, where each system or civilization must operate independently without relying on immediate external input. From a broader perspective, communication limits reinforce the isolation imposed by physical distance. Even though the universe is physically connected through space-time, the finite speed of information creates effective separations between regions. These separations are not absolute in a spatial sense, but functional in a temporal sense, as interactions become too slow to maintain coordinated relationships across large scales. As these constraints accumulate, communication becomes less about exchange and more about archival transmission of information across time. Signals become records of past states rather than tools for active coordination. This transforms interstellar communication into a delayed observational process rather than a dynamic interaction, reinforcing the broader pattern in which distance, time, and causality collectively limit the ability of any system to remain continuously connected across the vast structure of the cosmos. Navigation across interstellar space depends on precise understanding of position velocity and long-term trajectory stability within a dynamic and slowly evolving gravitational environment. In local space, navigation is supported by relatively stable reference points such as planets, moons, and nearby stars, whose positions change predictably over short timescales. However, as distance increases beyond a single star system, the reliability of fixed reference structures begins to weaken due to cumulative uncertainties in measurement, gravitational perturbations, and the long timescales involved in travel. At the outermost scale, interstellar navigation begins with star catalogues that map positions and motions of stellar objects within a galaxy. These catalogues are constructed using observations of parallax proper motion and spectral analysis, allowing astronomers to estimate distances and velocities of stars relative to one another. While highly precise in local regions, these measurements still contain small uncertainties that become significant when projected across light-year distances and extended timeframes. Over the duration of an interstellar journey, even minor errors in initial trajectory calculations can grow into large positional deviations. Space is not static but shaped by gravitational fields that extend across vast distances. Every star exerts a gravitational influence, and while these forces are often weak at long range, their cumulative effect over time can alter trajectories. In addition, large-scale structures such as star clusters, molecular clouds, and galactic arms contribute to subtle variations in gravitational potential. A spacecraft traveling through these regions does not move through empty space alone, but through a constantly shifting gravitational landscape that slowly modifies its path. Interstellar navigation must also account for the motion of target systems. Stars are not fixed points. They orbit the center of the galaxy and move relative to one another. Over the millions of years required for galactic evolution, stellar positions change significantly. Even over shorter timescales relevant to interstellar travel, a destination star system may shift by distances large enough to require continuous trajectory correction. This means that navigation is not simply aimed at a fixed coordinate, but at a moving target whose future position must be predicted far in advance. Predictive modeling becomes essential for long-distance navigation. Calculating the future position of a star system requires accounting for its velocity gravitational influences from nearby stars and its motion within the galactic potential. These calculations are based on known physical laws, but are still subject to uncertainties due to incomplete data and small measurement errors. Over long durations, these uncertainties accumulate, making precise targeting increasingly difficult as distance and time increase. Course correction in interstellar navigation would require periodic adjustments to account for these accumulating uncertainties. However, each correction introduces new dependencies on measurement accuracy, propulsion capability, and energy availability. Small deviations corrected early may prevent larger errors later, but the ability to perform such corrections depends on maintaining functional systems over long periods. In extended missions, particularly those spanning centuries, maintaining this level of control becomes progressively more difficult. Another factor influencing navigation is the interstellar medium itself. While extremely sparse, the presence of gas and dust can exert subtle pressure on a moving spacecraft. At relativistic speeds, even low-density regions can produce measurable drag or deflection effects over long distances. These effects are small at any given moment, but can accumulate over time, gradually altering trajectory unless continuously corrected. This introduces an additional layer of uncertainty that must be accounted for in long-term navigation planning. Gravitational lensing also affects the propagation of light used for navigation. As light passes near massive objects, its path is bent due to curvature of space-time. This effect can distort the apparent position of distant stars, making them appear slightly shifted from their true location. While this phenomenon is well understood and measurable, correcting for it across large-scale navigation requires precise models of mass distribution throughout space, which become increasingly complex over interstellar distances. The expansion of the universe introduces further complexity at the larger scales. Although galactic structures remain gravitationally bound, regions beyond local clusters are influenced by cosmological expansion. This expansion affects how distances are measured and how signals propagate across vast regions. While not directly relevant to navigation within a single galaxy, it establishes a broader context in which large-scale positioning becomes dependent on the dynamic structure of spacetime itself. As velocity increases toward relativistic speeds, navigation becomes increasingly sensitive to small errors. Relativistic effects alter time perception, signal timing and distance measurements, requiring constant recalibration between onboard systems and external reference frames. Even slight discrepancies in velocity estimation can lead to significant positional drift over long durations. This makes high-speed interstellar travel not only an energy challenge, but also a precision challenge where small errors propagate into large-scale deviations. Autonomous navigation systems would be required for interstellar travel due to the communication delays involved. These systems would need to operate independently, making real-time adjustments based on local measurements without external guidance. However, autonomy introduces its own limitations as decision-making must rely on incomplete information about distant targets and evolving conditions along the route. The longer the journey, the greater the reliance on predictive models that may diverge from actual conditions over time. Error accumulation becomes one of the most significant challenges in interstellar navigation. Small uncertainties in initial conditions, measurement errors, and environmental influences combine over time, producing deviations that grow unpredictably. Even with advanced correction mechanisms, the inability to continuously verify position against real-time external references limits the precision of long-distance travel. Over interstellar scales, these cumulative uncertainties can become large enough to significantly affect arrival accuracy. From a broader perspective, navigation in interstellar space reflects the interplay between order and uncertainty within a dynamic cosmic environment. While the laws of physics provide a stable framework for motion, the practical application of those laws over vast distances is constrained by incomplete information, environmental variability, and the limits of measurement precision. This creates a navigation landscape where trajectories are not fixed paths, but evolving approximations shaped by continuous interaction between prediction and correction. Within this framework, interstellar navigation becomes a process of managing uncertainty across time and space, rather than simply plotting a course between 2 points. The universe provides structure through gravity and motion, but it also introduces variability that grows with scale. As a result, any attempt to traverse interstellar distances must operate within a system where precision gradually erodes over time, reinforcing the broader reality that long-range travel is governed not only by physical law, but also by the practical limits of knowledge and control in an expanding and dynamic cosmos. Resource sustainability in interstellar travel represents the long-term ability of a closed system to maintain all essential inputs required for survival operation and stability without external support. In interstellar space, there is no practical possibility of resupply once a journey begins, meaning every necessary resource must be carried, recycled, or generated internally. This creates a self-contained dependency structure where energy, matter, and environmental stability must remain balanced across extremely long durations, often extending far beyond any engineered system tested in known human history. At the most basic level, life support systems require air, water, and food. Oxygen must be continuously available for respiration, carbon dioxide must be removed or recycled, and water must be purified and reused with high efficiency. Food production depends on either stored reserves or continuous biological cultivation systems. In a closed environment, these processes must operate in a tightly coupled cycle, where waste from one system becomes input for another. Even small inefficiencies in recycling can accumulate over time, gradually reducing available resources, unless perfectly compensated by regeneration systems. Energy is the central driver of all resource sustainability. Every recycling process, environmental control system, and biological function depends on continuous energy input. In interstellar contexts, energy must be generated on board, typically through nuclear systems or other long-duration power sources. Unlike planetary environments where external energy such as sunlight can be reliably accessed, deep space, travel reduces or eliminates consistent external energy availability. This forces reliance on internal reserves that must remain stable across entire mission durations. Any degradation in energy systems directly affects all other resource cycles. Material sustainability introduces another layer of complexity. Mechanical systems degrade over time due to wear, radiation exposure, thermal cycling, and microscopic structural fatigue. Components must be repaired or replaced using onboard manufacturing capabilities. This requires raw materials which must either be carried at launch or extracted from available sources such as captured interstellar matter or onboard recycling of existing structures. However, interstellar space is extremely sparse, making external material harvesting highly inefficient and unreliable. As a result, most material sustainability must rely on closed-loop recycling of onboard resources. Closed-loop recycling systems aim to minimize waste by continuously reprocessing materials. Metals, plastics, and organic compounds must be recovered and reused repeatedly. However, no recycling system operates at perfect efficiency. Each cycle introduces small losses, contamination, or degradation of material quality. Over long durations, these losses accumulate unless compensated by highly advanced purification and restoration systems. The challenge increases further when considering complex biological materials which are more difficult to fully recycle without loss of function or structure. Food production in interstellar environments relies heavily on controlled ecological systems such as hydroponics or synthetic biological habitats. These systems convert energy, water, and nutrients into edible biomass. However, maintaining stable agricultural cycles requires careful control of environmental conditions, including light, temperature, humidity, and nutrient balance. Over long durations, even slight imbalances in these conditions can lead to reduced yields or system instability. Additionally, biological systems are inherently variable, making long-term predictability more difficult compared to mechanical systems. Waste management is another essential component of resource sustainability. All biological and mechanical processes generate waste products that must be safely processed or recycled. In a closed environment, accumulation of waste cannot be allowed, as it would eventually disrupt system stability. Efficient waste conversion systems must therefore operate continuously, breaking down complex materials into reusable components. However, these systems themselves require maintenance and energy, adding to the overall resource burden. Redundancy becomes critical in sustaining resources over interstellar durations. Multiple overlapping systems are required to ensure that failure in one component does not lead to total system collapse. However, redundancy increases mass and complexity, which in turn increases energy requirements for propulsion and maintenance. This creates a structural tension between reliability and efficiency, where improving safety often increases resource consumption. The passage of time introduces additional sustainability challenges. Over decades or centuries, even highly stable systems degrade due to cumulative microscopic effects. Radiation exposure can alter material properties, slow chemical reactions, and damage electronic systems. Thermal cycling from repeated heating and cooling can weaken structural bonds. These gradual processes are difficult to fully prevent and must be continuously managed through monitoring and repair. Human factors also influence resource sustainability. Population size, consumption rates, and behavioral patterns all affect resource usage. Variations in consumption over time can create imbalances in tightly controlled systems. Predicting long-term human behavior within isolated environments adds uncertainty to resource planning, especially over multi-generational timescales, where cultural and technological changes may alter consumption patterns in unpredictable ways. Storage systems for critical resources must maintain stability over extremely long durations. Even when resources are not actively used, they must remain preserved without degradation. Fuel, biological materials, and spare components must be protected from radiation, temperature fluctuations, and chemical breakdown. Over long periods, even storage conditions can introduce slow degradation that reduces overall system efficiency. Another constraint arises from system interdependence. Resource systems are not isolated but deeply interconnected. Energy production affects water recycling, which affects food production, which in turn affects waste management and oxygen regeneration. A disruption in one subsystem can propagate through the entire network, creating cascading failures. This interconnectedness means that long-term sustainability depends not only on individual system efficiency, but also on overall systemic stability. From a broader perspective, resource sustainability in interstellar travel reflects the fundamental challenge of maintaining equilibrium in a completely closed system over extended time. Unlike planetary environments where external inputs continuously refresh ecological cycles, interstellar systems must operate without replenishment. This transforms sustainability into a problem of perfect long-term balance between consumption and regeneration, where even minor deviations accumulate over time. Within this framework, resource sustainability becomes one of the most restrictive factors in interstellar travel. It is not limited by a single bottleneck, but by the continuous interaction of energy, matter, biology, and time. As these elements remain in constant flux, maintaining stability across centuries or millennia requires a level of precision and resilience that increases dramatically with duration. This reinforces the broader reality that long-distance space travel is constrained not only by motion and energy, but also by the enduring challenge of sustaining life and machinery within an entirely closed and isolated environment. Gravitational complexities arise from the fact that space is not a passive empty backdrop, but a dynamic structure shaped by the presence and movement of mass and energy. In interstellar space, gravity operates across vast distances, subtly influencing trajectories, altering orbital paths, and shaping the large-scale architecture of galaxies. While these effects may appear weak when considered locally, their cumulative influence over long durations becomes a significant factor in any attempt to traverse interstellar distances with precision and stability. Every star generates a gravitational field that extends far beyond its visible surface. This field diminishes with distance but never fully disappears, meaning that even in seemingly empty regions of space, gravitational influence is always present. As a spacecraft moves through interstellar space, it is continuously affected by the combined gravitational pull of nearby stars, distant stellar systems, and the overall mass distribution of the galaxy. These influences overlap and interact, creating a complex and continuously shifting gravitational landscape. Within a single star system, gravitational interactions are relatively predictable. Planetary orbits follow stable patterns governed by the dominant gravitational influence of the central star, with smaller perturbations from other bodies. However, once a spacecraft leaves a stable system and enters interstellar space, it no longer follows a single dominant gravitational center. Instead, it moves through a multi-source gravitational field where no single object fully governs motion. This creates a more complex environment where trajectories are shaped by subtle and overlapping influences from multiple directions. The galaxy itself rotates with stars orbiting the galactic center in long, slowly evolving paths. This motion means that gravitational relationships between objects are not static, but change over time. As a result, the gravitational environment encountered along an interstellar journey is not constant, but varies depending on position and time. Over long durations, these variations can significantly alter a spacecraft's trajectory, requiring continuous adjustment or precise initial planning to account for cumulative deviations. Gravitational interactions are also influenced by large-scale structures such as molecular clouds, star clusters, and dark matter distributions. Molecular clouds composed of gas and dust can locally enhance gravitational fields and subtly deflect passing objects. Star clusters contain densely packed groups of stars whose combined gravity creates complex internal dynamics. Dark matter, though not directly observable, contributes additional gravitational influence that affects the motion of visible matter throughout the galaxy. Together, these components form a gravitational environment that is highly structured, yet not easily predictable at fine scales. As a spacecraft moves through this environment, it experiences continuous gravitational perturbations. These perturbations are typically small at any given moment, but can accumulate over long distances, gradually altering velocity and direction. Even minor deviations in trajectory can become significant over interstellar scales, where distances are measured in light years. This means that precise navigation must account for not only initial conditions, but also the cumulative effect of gravitational interactions throughout the entire journey. Gravitational lensing adds another layer of complexity. When light or other signals pass near massive objects, their paths are bent due to space-time curvature. This effect can distort observations of distant stars, making their apparent positions slightly different from their actual locations. For navigation systems that rely on electromagnetic signals, this introduces potential errors in position estimation unless carefully corrected. While the effect is well understood in principle, applying corrections across vast and dynamic gravitational fields remains a complex challenge. At relativistic speeds, gravitational effects interact with time dilation and motion in non-intuitive ways. The curvature of space-time means that trajectories are not simply straight lines through space, but geodesics that represent the most natural paths through curved geometry. As velocity increases, these geodesics become increasingly sensitive to small variations in gravitational fields, making high-speed navigation more susceptible to deviation. Even minor gravitational influences can produce significant long-term changes in trajectory when combined with relativistic motion. Gravitational assists commonly used within star systems rely on carefully timed passes near massive bodies to alter velocity and direction without expending additional energy. While effective within planetary systems, applying such techniques across interstellar distances becomes far more complex due to the scarcity of suitable gravitational sources and the unpredictability of their distribution along a given path. The absence of frequent, well-positioned massive bodies limits the ability to use gravity as a practical navigational aid over long distances. Another important aspect of gravitational complexity is the influence of cumulative uncertainty. Because gravitational fields are the result of many interacting masses, even small errors in estimating mass distribution or position can lead to long-term deviations in predicted trajectories. Over interstellar timescales, these small uncertainties compound, making exact prediction of long-range paths increasingly difficult. This reinforces the need for continuous correction systems, which themselves depend on accurate measurements and stable onboard computation. Gravitational time effects also play a role in navigation. Time passes at different rates depending on gravitational strength, meaning that clocks in stronger gravitational fields run slightly slower than those in weaker fields. While these differences are small in most interstellar environments, they become relevant when high-precision timing is required for navigation communication or synchronization between systems operating under different gravitational conditions. The large-scale structure of the galaxy introduces additional gravitational asymmetries. Spiral arms, for example, contain higher concentrations of mass and star-forming regions, while interarm regions are more diffuse. These variations create uneven gravitational potentials that influence the motion of objects over long distances. A spacecraft traveling through different regions of the galaxy would therefore encounter varying gravitational conditions that gradually reshape its trajectory. From a broader perspective, gravitational complexity illustrates the deeply interconnected nature of motion in the universe. No object moves in complete isolation. Every trajectory is influenced by the combined mass of surrounding structures, both visible and invisible. This means that interstellar travel is not simply a matter of moving through empty space, but of continuously interacting with a dynamic gravitational network that extends across the entire galaxy. Within this framework, gravitational effects do not act as a single obstacle, but as a continuous shaping force that influences every stage of interstellar motion. The universe provides structure through gravity, but that structure is neither simple nor static. Instead, it forms a constantly evolving environment in which every movement is part of a larger gravitational system that cannot be fully isolated or simplified over extreme distances and timescales. The probability of failure in interstellar travel is not a single point of risk, but a cumulative outcome that emerges from the interaction of all previously described constraints across time distance and system complexity. In a local environment, failure can often be isolated, corrected, or contained. However, in interstellar space, every subsystem operates under continuous stress without external support, and every small imperfection has the potential to propagate across vast durations. This transforms failure from an event into a gradually increasing likelihood, shaped by the compounding effects of physics, engineering limits, and time. At the outermost level, failure begins with launch and acceleration. Any interstellar mission must first overcome planetary gravity, atmospheric resistance, and structural stress during initial propulsion phases. These early stages already contain multiple critical thresholds, where minor deviations can determine long-term success or failure. Once a spacecraft enters interstellar trajectory, it becomes fully dependent on onboard systems, meaning that any unresolved issue at launch cannot be externally corrected later. This creates a front-loaded vulnerability where initial conditions heavily influence eventual outcomes. As travel continues, the long duration of exposure introduces a continuous probability of system degradation. Mechanical systems wear down through friction, vibration, radiation exposure, and thermal cycling. Electronic systems experience gradual signal degradation due to cosmic radiation and material fatigue. Biological systems, if present, undergo aging and adaptation pressures that may reduce long-term stability. Each subsystem carries its own failure modes, but in a closed interstellar environment, these modes are not independent. A failure in one area can cascade into others, amplifying overall risk. Redundancy is often used in engineering to reduce failure probability, but in interstellar conditions, redundancy itself becomes a source of complexity. Additional systems require more mass, more energy, and more maintenance, each of which introduces new potential points of failure. Over long durations, redundant systems may also degrade simultaneously due to shared environmental exposure. This means that redundancy reduces immediate risk, but does not eliminate long-term cumulative probability of breakdown. Radiation exposure contributes significantly to failure probability. High-energy particles can damage structural materials, disrupt electronic systems, and degrade sensors used for navigation and communication. While shielding can mitigate these effects, no known shielding system can fully eliminate exposure over extremely long timescales without becoming prohibitively massive. As exposure continues, small errors in system performance accumulate, increasing the likelihood of critical malfunction in navigation, propulsion, or life support systems. Navigation errors also contribute to long-term failure risk. Small deviations in trajectory can grow over time due to gravitational perturbations, measurement inaccuracies, and limited correction opportunities. Even minor miscalculations in velocity or direction can result in large positional errors over interstellar distances, potentially causing a spacecraft to miss its intended destination entirely. Because real-time external correction is impossible due to communication delays, these errors must be managed autonomously, increasing reliance on onboard predictive systems that themselves carry uncertainty. energy system failure represents another major risk factor. Interstellar missions depend on long-duration energy sources that must operate continuously without external replenishment. Any degradation in energy production, storage, or distribution can cascade through all dependent systems. Reduced energy availability affects propulsion, environmental control communication, and computational capacity. Over time, even small inefficiencies can accumulate into critical shortages, especially if energy demands fluctuate due to environmental or operational changes. Material fatigue plays a similarly important role in long-term failure probability. Structural components are subjected to continuous stress from acceleration thermal cycling and microscopic impacts from interstellar particles. Over time, these stresses create microfractures and weakening of materials that are not immediately visible, but gradually reduce structural integrity. Eventually, these small defects can combine into larger structural failures, especially under dynamic load conditions or during course correction maneuvers. Biological and ecological systems, if present, introduce additional layers of uncertainty. Closed ecosystems must remain stable over extremely long periods, but biological processes are inherently variable. Small imbalances in microbial populations, nutrient cycles, or environmental conditions can accumulate into larger systemic instability. In multi-generational scenarios, demographic changes and genetic drift further increase unpredictability, making long-term biological stability difficult to guarantee. The interaction between subsystems amplifies overall failure probability. In tightly coupled systems, a malfunction in one area can propagate through multiple dependent systems. For example, a failure in energy production can affect life support, which in turn affects biological stability, which may further impact human operation of maintenance systems. These cascading interactions mean that interstellar spacecraft are not simply collections of independent systems, but integrated networks where failure propagation can accelerate over time. Time itself acts as a multiplier of failure probability. The longer a system operates without external intervention, the greater the chance that some component will degrade beyond operational limits. Even systems designed for extreme reliability cannot avoid this fundamental relationship between time and entropy. Over interstellar timescales, this results in an unavoidable accumulation of risk that cannot be fully engineered away, only managed or delayed. Environmental unpredictability adds further uncertainty. Interstellar space contains regions of varying density, radiation intensity, and gravitational complexity. While many of these variations are sparse, their cumulative effect over long distances introduces unpredictability into long-term mission outcomes. A spacecraft may encounter regions of higher than expected radiation or dust density that accelerate wear and increase system stress beyond planned thresholds. From a probabilistic perspective, the overall likelihood of mission failure increases as a function of time distance and system complexity. Each additional year of operation introduces new opportunities for error degradation or unexpected interaction. Even if individual systems maintain high reliability, the combined probability of at least one critical failure event approaches certainty over sufficiently long durations. Within this framework, interstellar travel is not defined by a single point of success or failure, but by a continuous process of risk accumulation across multiple domains. Every subsystem contributes to the overall probability landscape, and no system operates in isolation from the others. The result is a deeply interconnected structure where success depends on maintaining stability across energy structure, biology navigation, and environment simultaneously over vast periods. Ultimately, the probability of failure reflects the fundamental challenge of sustaining complex systems far beyond their original design environment. The universe imposes continuous constraints through radiation, gravity, distance, and time, while engineered systems must operate without interruption across scales that exceed any natural or technological precedent. In this context, failure is not an isolated possibility, but an emergent property of sustained existence in an environment where every factor gradually contributes to increasing uncertainty over time and distance. The observable universe constraint represents the outer boundary of all possible interaction, defined not by technology or engineering, but by the finite age of the universe and the speed at which information can travel through space-time. Every region of the universe that can be observed is limited by how far light has had time to travel since the beginning of cosmic expansion. This creates a horizon beyond which no signal, object, or influence can reach an observer within the current age of the universe. In interstellar terms, this establishes a fundamental limit on connectivity that extends far beyond individual star systems or galaxies. Within the observable universe, structures are arranged in a hierarchy shaped by gravity and cosmic expansion. Galaxies form clusters, clusters form filaments, and vast voids separate these structures into regions of differing density. Although these regions are physically connected through space-time, their ability to interact is constrained by the finite speed of light and the expansion of space itself. As a result, distant regions evolve independently, with no practical possibility of direct influence once separation exceeds certain cosmological thresholds. Cosmic expansion plays a central role in defining this boundary. Space itself is stretching, causing distant galaxies to recede from one another. In many cases, this recession occurs at effective speeds greater than light, due to the expansion of space rather than motion through space. This does not violate relativistic limits, but it does create regions of space that become causally disconnected over time. Once a region passes beyond this boundary, signals emitted from it can never reach an observer no matter how much time passes. This expansion introduces a dynamic horizon that changes over time. As the universe ages, some regions move out of contact while others remain accessible. However, the overall effect is a gradual increase in isolation between distant cosmic structures. Even within a single galaxy, long-term evolution continues under gravitational binding, but interactions between galaxies become increasingly limited as expansion dominates large-scale structure. This reinforces the separation between regions of the universe and further constrains any form of interstellar or intergalactic travel. In this context, interstellar travel is not only constrained by local physics, but also embedded within a larger cosmological framework that defines what regions are accessible in principle. Even if a spacecraft could achieve extremely high speeds, it would still remain bound by the structure of space-time and the expansion of the universe. Certain destinations are not merely difficult to reach, but fundamentally unreachable due to causal separation. This means that the universe itself contains regions that are permanently isolated from one another, regardless of technological advancement. The finite speed of light ensures that all observations are delayed representations of reality. Every image of a distant star or galaxy shows its past state rather than its present condition. As distance increases, this delay grows until it spans billions of years. In some cases, the light observed today left its source before planetary systems like Earth even formed. This temporal depth transforms the universe into a layered structure of past states, where observation becomes a form of time-delayed reconstruction rather than real-time awareness. Interstellar distances within a galaxy, while smaller than intergalactic scales, still fall within this same framework of delayed interaction. Even the nearest stars exist in a regime where direct communication or travel requires years or longer. As discussed across earlier sections, this delay compounds with energy constraints, radiation exposure, gravitational complexity, and resource limitations. When combined with the cosmological horizon, these factors reinforce the conclusion that large-scale traversal of the universe is not simply a matter of overcoming distance, but of operating within a fundamentally time-limited structure. The observable universe also defines a limit on information exchange. Any signal sent from beyond the cosmological horizon cannot be received, meaning that knowledge of those regions is permanently inaccessible. This creates a boundary not only of physical travel but of understanding. The universe beyond this limit may exist in a physical sense, but it cannot interact with the observable region in any meaningful way. This separation is not due to technological deficiency, but to the structure of space-time itself. Within all these constraints, hypothetical interstellar civilizations would still be confined to local regions of gravitationally bound space. Galaxies and clusters remain internally connected, but beyond these structures, expansion dominates and interaction fades. Over extremely long timescales, even galaxies may become isolated islands of matter, surrounded by expanding emptiness, reinforcing the long-term trend toward separation and loss of contact between regions of the universe. From a physical perspective, this final constraint ties together all previous limitations: energy, propulsion, radiation, biological stability, communication, delay, navigation, uncertainty, gravitational complexity, and failure probability. All operate within a universe that itself imposes a boundary on what can be reached or influenced. The observable universe is not just a spatial limit, but a temporal and causal one, defining the ultimate extent of possible interaction. In this framework, the impossibility of interstellar arrival at distant targets becomes not a single restriction, but the combined outcome of multiple reinforcing layers of physical law. Each constraint strengthens the others, forming a structure where increasing speed, distance, or complexity does not remove barriers but amplifies them. The universe therefore maintains a consistent structure in which motion, information, and causality remain bound within finite limits, ensuring that all processes unfold within a coherent but inherently restricted cosmic framework. The final reality is that interstellar travel exists within a universe defined by separation as much as connection. Space allows motion, but it also enforces distance. Time allows progression, but it also imposes delay. Energy allows transformation, but it also enforces cost. Across all scales, these relationships remain consistent, shaping a cosmos where every journey is bound by the same fundamental rules that govern light matter and space-time itself. In this structure, the idea of reaching distant stars becomes not a matter of capability alone, but a reflection of the deepest limits embedded in the fabric of reality.